is going to present her senior thesis on mitigating current variation in particle beam microscopy. She's advised by Professor Vivek Goyal. And I don't know if Vivek, you have something to add to the introduction, or should we just start?
Well, I didn't have a prepared introduction, but I'll just say that it's been a great pleasure to have Luisa in the group. She quickly progressed from EK381 student to EK381 UTF to member of the group who's made really great contributions on this project. Luisa, please take it away.
So yes, hi everyone. My name is Luisa, and the title of my thesis project, my senior thesis project, is Mitigating Current Variation in Particle Beam Microscopy. So the first question you're probably thinking is, what is particle beam microscopy? So essentially, it's an imaging and a fabrication technique at near atomic resolution, meaning that we have very small samples that we're trying to either get images of or fabricate in certain ways. And they're very, very small, so they're near atomic. So this method is doing it at that resolution. This is used in a whole wide range of fields, including material science, where we're trying to understand more of what these very microscopic samples look like and discover more things about them. Also semiconductor manufacturing. So this is more the fabrication side. Even biological sciences, like food science, for example, even used in medical science, for example, even in, this is used somewhat in our current pandemic for some research of the SARS-CoV-2 virus. And then even forensic investigation, because this whole idea is trying to see what very, very small samples look like. So you may be thinking you have an idea of what a microscope is, which you're probably thinking of a microscope you look through, which is actually an optical microscope where it uses light so we can see with our eyes what the sample looks like. But these type of microscopes are because the samples are so small, we can't use light, so we use particles, and the way they interact, we can create images and reconstruct those to see what these samples look like. So this is essentially what particle beam microscopy is. But as I go through this presentation, I first will explain more of the details of how particle beam microscopy works. Then I'll talk about the variation. In my title, I do have particle beam variation in there and how that affects the reconstruction of these images. Then I'll be talking about a specific type of measurement called time resolved measurement that is used in the scenario of particle beam microscopy. Also the robustness of this measurement to the variation of beam. And then I will talk about the main component of my project, which is the design of a new joint estimator algorithm, which I'll explain in more detail later. And lastly, I'll be going through simulation results of how this algorithm performed. So again, first we're going to be starting with how does this whole scenario look like? So again, we have, as I mentioned, this is not an optical microscope. We're dealing with a particle beam microscope where we have this particle beam generator. And the idea is that we have this true sample and we don't know what it looks like. The whole idea is we're trying to reconstruct an image here of what it looks like. And what we have in this in this setup is we have this generator that generates a beam of particles. So we go across the sample in a raster scanning fashion, meaning we go across with the particle beam. And we have particles that are shooting out and they're hitting the sample. And we can call, well, I'll be calling this the dose. We have this dose value that's given and it's shooting particles at the sample. Now there's some dwell time per pixel. Since we're recreating an image, we have obviously a certain number of pixels, and they map to obviously the in the sample. And as we go across the sample with this beam, we have a specific dwell time that's the same for every single pixel. And then in response, so as I mentioned, we have particles, we're shooting particles at the sample.
Oh, that's it. I had to turn my sound on.
And in response to the
I would be mute,
particles
but you
that
wouldn't
we get secondary electrons that are detected, meaning that, so what happens is we have particles hitting the sample, and then we get, in response, because of this reaction that happens, we get a burst of secondary electrons. And this is what's detected, and that's actually what is used to recreate the image, because these detected secondary electrons map to grayscale levels. And that's the information that's used to reconstruct the image of this sample. Now, what's important to note, though, is that both the particles that are coming out of the particle beam generator and the burst of secondary electrons for a specific particle are both Poisson random variables. So that just means that they're random in nature, that's what makes this process, it's one of the difficult parts of it, meaning that the detected total secondary electrons is a compound Poisson process. So there's definitely a lot of randomness here. But again, so the main idea of this particle beam microscope is we have our generator, we're shooting particles at a sample as we go across it. And in response to each particle, we get a burst of secondary electrons, and we can use those electrons to reconstruct an image so we can see what the sample looks like. And these incident particles can be electrons or helium ions mostly. So if there are electrons that are being shot at the sample, it's called scanning electron microscopy, or SEM. And if we use helium ions, it's helium ion microscopy, or HIM, where the only difference is the size of the particles. So the electrons are very, very small. And that just means because they're so small, we get fewer secondary electrons. And later, when I go through my simulation results, I'll actually be showing an example of each of how the different number, how it can be more difficult when we have fewer secondary electrons, meaning less information, how we can still try to reconstruct images of what those samples look like. So this is the particle beam microscopy setup. Now if we'll go into, what about this beam current variation? So I haven't talked much about that yet. So beam current variation, again, as I mentioned, we have this dose. Now, although it would be ideal that as we're going across this sample, as we're raster scanning, that the dose value would be the same, in reality, this beam current actually varies in time, meaning as we're going across, the dose you give to the previous pixel will most likely be different in the next sample, just because of the natural phenomenon that happens, that it's not perfect. And this is a way of, this is an example, which actually goes along with my results that I'll show later, that this is, if this is the sample and it's this size, this is what the dose looks like. Meaning, if you see, we have these horizontal stripes because we're horizontally scanning across. And this is what the dose looks like, where the lighter the value, the lighter the stripe is, the larger the value of the dose is, versus the darker values are lower values of dose. So yes, this is the particle beam dose. And as you see, it's changing as it's going across the sample. And very, very often there's this false assumption that this beam current, again, is one constant value. So it's assumed that it's one value, but it's actually has this effect if it's different. As we're going across the sample, it's changing. So this leads to, if this is our reconstructed image, if you see these stripes, you can see how they affect the reconstructed image, because we have these darker stripes which go along with these darker stripes in the reconstructed image. And so the way these stripe artifacts are coming from the fact that the raster scanning is faster than the beam current variation, which gives us these striped artifacts, which, although in an image like this, where you may be thinking, well, this sample, it looks like it should just be this, this portion, and these stripes don't really like it makes it harder to see the image, but I can still kind of see what the image should look like. But the major issue though is if the sample we're trying to look at actually has stripes in it, if there are striped artifacts, it's hard to tell whether are these stripes from the beam current varying or are they actually in the sample, and that can be a big question and be really tough then to figure out what the sample looks like. Now on the other end, as I mentioned, there is another side which I didn't focus on as much as the imaging, but there's the fabrication side of particle beam microscopy. And this is, again, where the particle beam, instead of trying to reconstruct an image, it's trying to manipulate the sample's actual structure, meaning we're using the beam to actually change what the sample is. So this is for like semiconductor manufacturing, as I mentioned. That's an example. And this process is called milling, because we're actually changing or manipulating what the sample looks like. So this is an example of that, where we still have these stripes, but in this case, where this is still a reconstructed image though, this actually is, in this scenario, an accurate representation of this is what the sample actually looks like. But we don't want to have these stripes. If we're trying to recreate, or if we're trying to manipulate the sample in a specific way, but the beam current is not what we want it to be, we could be doing a lot more than we want. If the dose is higher than we think it is, then this can have these striped effects. So these are obviously very undesired. We don't want to have these stripes. So although the results are the same, where you see the stripes, this is actually in response to the milling, where it actually does look like versus in the image reconstruction, where that it's just from the way that it's being reconstructed and the way it's assuming that the dose is constant. So these are the effects of beam current variation. But now if I go into the next part is if we think about the measurement and how this is being used to actually, and this, again, I'll mostly be talking about the image reconstruction. So if we think about the measurement of how is this being used. So for this slide, if you notice this animation, I've stopped it. So we're frozen at 1 pixel. So as mentioned previously, we're scanning across the sample and we're shooting particles and getting secondary electrons in response. But in this case, in this slide, I'm just going to focus, if we zoom in on 1 pixel, what is happening there. And in this case, as I mentioned previously, these incident particles can be electrons or helium ions. But in this example, you'll see it says ions. So this is, it can be used also for the electrons, but it's an HIM or helium ion microscopy example. So first, if we go more in detail, I have some variables to talk about. So first, as I mentioned, we have particles coming out of the beam generator, and there are m number of particles. So that's how many particles there actually are. And then we have this variable called lambda, which is the mean of m, and that's what I'll be calling the dose. So from now on, when I say the dose, I'm not talking about the number of particles, but this mean value, lambda. And here, this is just an abstraction, a way to visualize what's happening. So again, as I mentioned previously, we have a dwell time for each pixel. And since we're frozen at 1 pixel, just think we're stuck on 1 pixel, and this is what's happening there. So here, each yellow arrow here is representing a particle, or in this case, it says ion. It's representing an incident ion that's coming out of the generator. And in response, for every single ion, we get a burst of these secondary electrons. And again, so if we have 4 in this case, we can see a burst of secondary electrons that comes for each incident ion. Now, the conventional measurement is to sum across all of these different clusters of secondary electrons. So that's all that's seen is this Y value, which is a sum. So the only thing that's seen that we would see in response would be this 13, that there's 13 of these secondary electrons. Now, what we actually want to know, though, is the mean of the way they're distributed. So the mean of each xi, where each xi is the burst, is how many secondary electrons are coming off in response to a specific ion. And that mean value is called eta. And that's actually, that's how we estimate the image, is we want a specific eta value for the pixel. So there are true eta values here that we're trying to estimate, and we estimate them by using these secondary electrons, which are related to the secondary electrons per ion in this specific way. So again, this is called conventional measurement because we just have one value, and it's what's most easily done is just to take this one value for every single pixel and just see how many electrons come off in total. Now, contrary to that, there's a more recently introduced way of measuring that's called time-resolved measurement. And the way this works is we still have this is the same scenario. We have the same number of ions and bursts of secondary electrons per ion. But the idea here is that we have n number of subacquisitions. And the idea for time-resolved measurement is that if we're able to break up the dwell time into n different sections, we can have a better idea of how many ions, or in this case ions, or in general particles, there are that are coming out of the beam generator. So in this way, instead of just having one y value, we have a vector. We have a vector that's n long, where we can see, oh, if there's a burst here, there's none here, there's probably an ion here, there's probably an ion here. And the idea with this measurement is that if we have a better idea of how many, if we're able to have a better idea of how many ions there are, then that means we have a better idea of what the dose is. And the more we know about the dose, the better we can estimate this eta value, which again, we're trying to get an eta value for every single pixel. So that's why this measurement is actually does a much better job, which I'll show in a minute, of this type of measurement that is able to split up the dwell time into these different subacquisitions. Now, these different measurements, they aren't the estimators themselves, they're just ways of collecting the data, but they each are analogous to specific estimators. So the conventional measurement goes with this conventional estimator, which it just takes this one y value, and it divides it by the dose. And that gives us our eta, which again, and I have a hat here, meaning this is an estimate versus the true eta. So this is what's done at each pixel. Versus the time-resolved measurement, what that does is there's actually multiple different algorithms that are associated with this measurement, but I will be focusing on the specific one that has proved to do the best job, is this time-resolved maximum likelihood estimator, which essentially, it's a very long name, and I'll just be referencing it as TRML. And this idea is essentially, it's a maximum likelihood estimate of, it takes a product of the probability mass function across all of the different subacquisitions, because as I mentioned, we have n of those. But yes, so this is just the specific estimator that uses this measurement and is able to get an estimated eta. And as mentioned, we're still frozen at 1 pixel, so this gives us an eta estimate at the pixel, and this is done at every single pixel. And if you notice, both of these estimators are falsely assuming that the beam current is known. So they have lambdas in here, which you remember lambda is the dose. But as mentioned, the beam current is actually varying. So this is where my project comes in, of what I've been able to add to this. But they're both making these false assumptions. So again, that leads into the main focus of my project. So the first is just, I went into looking at the robustness of this measurement and all the associated algorithms it has to this unknown and variable beam current. And then I went into joint estimation of both the image, where we're trying to get an eta value for every single pixel, and the incident ion dose or particle dose, lambda. And the algorithm that I'm proposing is I'm calling the sequential filtering algorithm that actually has two pieces, where the one piece it's trying to estimate the dose using a linear estimator, and the other one is using that previously mentioned TRML method for eta. So if we look first at the first, what I mentioned I first did was the robustness of the time result measurement. So here we're again want to emphasize we're frozen at 1 pixel, and this time resolved measurement algorithm, so the TRML, doesn't even try to estimate lambda. It makes this false assumption, but it's able to have still substantial improvement in the reconstructed image quality than the commonly used methods. So for this example, I will be using, as I've mentioned, the true dose is lambda, so that's the beam current, versus what the estimator thinks it is, I'll be calling lambda bar, which is just off by this error value epsilon. So here, if we look at this plot, I have a plot of the MSE, which is mean square error. It's just a measurement of how much we're off of the true value of eta. And here I'm plotting that versus epsilon. So that means here at 0, that means the estimator knows exactly what the dose is and it's using the correct one, versus as we go across, the larger the epsilon value is, or in this direction also the smaller, the farther away we are from the actual true dose, meaning the estimator is using the wrong dose. So I have the two lines here. So the conventional estimator that I showed on the last slide, you see does a very poor job of estimating when it doesn't know the beam current. Versus this TRML method, in comparison, if you just compare in this way, it looks flat. But if you zoom in, we're able to see it, of course, has a minimum at 0 when it does use the correct dose. But what's very, very important to emphasize the fact, though, is that when the conventional knows exactly what the dose is, meaning it has perfect knowledge, it still does way worse than this TRML method does when it is extremely off. So that just shows, again, this is demonstrating just how robust this time resolved measurement, and specifically this time resolved associated algorithm, is to beam current variation. And this was great to see, and this is just the beginning of, like, this led into my design of what I'm contributing for my project. So I'll now be going into the joint estimator algorithm design that I have, where my objectives are, one, to generate higher quality image reconstruction, again, to be able to reconstruct those images and try to get rid of those striped artifacts, but then also the estimate the dose, which is useful, of course, to estimate the image, but also it's very useful when trying to fabricate the samples and change them in different ways. Now, in terms of higher quality image reconstruction, this means I'm trying to get the lowest possible mean squared error for this model. And what does that mean exactly, lowest possible? I'll be trying to get within 20% of the minimum, where the minimum is if the dose were perfectly known. And then in terms of estimating the dose, this is actually a novelty. This hasn't really been done before, but I'm just trying to improve upon the baseline estimator for the dose lambda, which I'm comparing against one that I've come up with that's analogous to the conventional estimator that I mentioned previously, which is just flipping around this fraction, which this is just a quick and easy way to get a lambda estimate. And then, of course, what this algorithm is actually doing is it's a joint estimation. So it's estimating both the image and the incident particle dose. So both eta, where we want an eta value for each pixel, and lambda. So that's the dose. And again, this algorithm is called sequential filtering algorithm. Now, if we go through and I'm now going to go through a block diagram of how this algorithm works. So there are a lot of variables here. I just wanted to have this key if it's helpful. But we start off, we're lambda tilde. Again, we're trying to get this eta value per pixel, and this dose is lambda, but it's changing in time. So what we actually know at the beginning is just this lambda tilde value, which is the mean. So this constant value we're assuming. Then we have Y, which, if you remember, is the detected secondary electrons. And since we're looking at an entire image, we actually have a matrix here because we have P pixels. But then for every pixel, because this is time resolved measurement, we have N sub-acquisitions. So this is an N by P matrix. And then of course we know how many sub-acquisitions. So we use this value of the dose and what we've measured, the secondary electrons. And the first piece of the algorithm is to estimate eta. So using this TRML method, because as shown on the last few slides ago, that it does a very good job. And we're able to get this estimate of eta and for a specific iteration K. In this case, it's the first iteration. Then we're able to use the same data that I plugged in for the TRML, and using that data and this output from the TRML, we're able to, this is the newer piece, is a sequential filtering that's able to estimate lambda using this data. And the output of that is an estimate of lambda, again, for the same iteration of the algorithm. And then the idea of this algorithm is if instead of using the lambda tilde, if we then take this lambda hat value and plug it into TRML, that means we're using a better value of lambda because it's more accurate. And then we can get a better value of a closer, more accurate value of eta for the next iteration. Same here, we won't use the lambda tilde, we use the estimate, which then we have this iteration and we have an even better estimate of lambda. And this keeps going, this algorithm keeps going until at some point we've like reached an asymptote and the changes are so minute that that we can stop the algorithm. And if you're curious, the actual sequential filtering looks like this, where it's a linear estimator in Y because we have these secondary electrons, and L here is an iteration of the filter. So we're iterating through the algorithm by K, and this within, as we're filtering through, we're going through the image. So L goes from 1 to P because we go through all the pixels. So yes, we run through each pixel of the image to get an estimate of lambda for the dose for every pixel. And lastly, I'll be going through simulation results. I'll be going through 2 examples where, as I've shown previously, we have our dose and our image, and I'll be showing those where I'll show 2 examples, HIM, which if you remember is using the helium ions, which are larger, and then SEM, which uses the electrons, which are smaller, which is a more difficult problem. But before I go into that, there's also a method that I'm competing with. That's called DFT Domain nulling that takes the conventional estimate and tries to clean up the stripes. So this is an example of a conventional estimated image, and it uses a 2D fast Fourier transform. So it takes this conventional image, transforms it into the Fourier domain. And this is pre-filter. Then it's able to filter out the horizontal contributions. So if you see, there's this vertical stripe here that's faint. It filters that out, and then it transforms it back, and this is the result. So the idea here is it looks at this image and tries to take out the stripes. So this, of course, is dependent on each image, and the issue with this, of course, is if the stripes are actually part of the sample itself, this method could take out too many stripes. But this is the most commonly used method to deal with beam current variation. But now, again, we'll go into the results. So first is the HIM example, where I'll be going through the image estimates. We're here, the eta values, which again is what we're trying to estimate. These are the ground truth values, are larger because we are using ions, and those are larger. And we have these 3 sections. We have the conventional methods. This orange section is what are my novel contributions, and then these are the unattainable. I've shown this multiple times, that we have our ground truth image. This is the conventional estimated image. This is the DFT domain nulling. This is the TRML neglecting the dose. So this is what I had shown on that plot. This is the sequential filtering algorithm. So if you see, we're able to do even better. And then what's the unattainable is this perfect knowledge of the dose, where if there's still some error, but knowing the dose, we're able to do such a better job. And the idea here is that I'm trying to get as close as here as possible. And actually, to make it easier to understand, I also have some relative MSE. So if you replace these values, because they can be hard to try to subtract in our heads to see how close we're getting. If you see that if we're trying to get as close to here as possible, and my goal was to get within 20%, and actually do much better than that. I'm able to get really close to what I can do with perfectly knowing the dose. So these are the results for the HIM for the images. And then for the same data, we also have our 3 sections, and we have our ground truth dose. This is the baseline, which, as I mentioned, is just something to compare to. And then I have two examples of using the algorithm, where the first one is that our assumed dose is actually off by 2 standard deviations, meaning we're starting off with a really wrong value of the dose, but it's still able to do a much better job than the baseline, versus when we actually start with the correct constant value, then it's able to do even better. So if you this is again a novelty of estimating the dose. And then the only last thing I have is the same idea, but we have SEM, which again, SEM is using electrons as the incident particles, which means that the eta values are even smaller. So it's actually a much more difficult problem. So we have a different ground truth where we have still a conventional estimator, the DTFT, which tries to clean up the stripes, the robustness of the TRML that doesn't think of the dose, then the my algorithm that actually tries to estimate it, and then the perfect if the TRML estimator knew it perfectly. And if you notice, the stripes are very hard to see because SEM is a very difficult problem and they're so similar, where again, if we look at the relative MSEs here, they're so small, and there's hardly a difference. But if you notice, my algorithm is very, very close to knowing perfectly what the dose is, which just shows how great of a job that the algorithm can do. And then along with that, we have our dose estimates, where we have our ground truth, the conventional or baseline that I'm comparing against. And again, we have 2 examples where we have using the wrong constant value that's off, and then the correct constant value. But it's still, the algorithm does a much better job than anything that's been done. And honestly, not much has been done in trying to estimate the dose before. So it's a true novelty. But yeah, so these are my results. And in conclusion, so I definitely completed my goals of generating higher quality image reconstruction and estimating the dose, which means that this beam current variation really can be mitigated. And in the past, to deal with it, to try to lessen these effects, in the lab, expensive particle beam generators have been used to try to try to make it so exact, so they're very precise. But using these methods, if we can then deal with it, then they don't have to be so precise, meaning they don't have to be so expensive. But yes, and then I just want to acknowledge some people. Obviously, I want to acknowledge my thesis advisor, Professor Vivek Coyle, just for helping me throughout this whole year. My mentor, Sheila, has been a huge help too. And then also Mingshu and Akshay in the group, who are always helping me every week throughout this year, have been super helpful. So I'm super grateful to them, and also everyone in our entire research group. Yes, just thank you. I'm very flattered that y'all wanted to come and listen to me talk about my project. Just thank you so much for listening. I really do. I loved spending this year working on this project. So please, if you have any questions, I'd love to answer them and talk about them. But yes, that's all I have. So thank you for listening.
Thank you, Luisa. Very nice. Any questions?
Well, maybe I should look at the chat.
I have just a real quick question.
Mm-hmm.
Not really so much a question. Can you go back to your conclusion slide for just 1 second?
Mm-hmm. Oh, just a second. Here. Mm-hmm.
Okay, thank you so much. I sort of.
Oh, sorry if I went through fast. Yeah.
Luisa. This was really great, and yeah, just great work overall. I had one question about the parameters eta and lambda, because it seems like having multiple parameters, it's kind of hard to understand when something is going to perform well or not. So is there like a challenging region if lambda is too low? Does it become harder to estimate, or is it kind of the opposite if lambda is too high? Have you seen any of those sort of trade-offs in the filtering? Or is there like a sweet spot at a certain set of values that it does pretty well?
Yeah, to be honest, to make these fair like comparisons, when the hardest thing is when the values of eta are really, really small, and to combat that, I use larger values of dose. So for example, if I because they were in the top corner, I use larger values of a constant value of like the mean of the dose is larger when I have the smaller eta values versus like all the way back. This is still the same one. Sorry, there's a lot of animations versus here, it's smaller.
Okay.
So it's more, what's the most challenging is more the parameter eta than lambda. And because eta, of course, is within the sample itself, so that can't really be controlled. But what we can control is the dose that we give it. So yes, if I use a too small value of the dose, I don't get enough information because I don't have as many particles hitting the sample. And then actually, if I make the dose way too big, that means I'm shooting all these particles, and actually it can damage the sample. So, but it's the biggest concern is more eta because we can't control that.
Great, thanks for your answer.
Other questions?
Hey, Luisa. This is a nice presentation, by the way. I was just wondering, so does this happen in real time as the machine is like scanning the substance, or is this with data that's already been collected and done in like post-processing?
Which this kind of also answers the question in the chat, but I did use MATLAB for these simulations. So within these simulations, of course, as we're going through, we are estimating like the image, like we take the measurement, we measure it, and then we afterwards then we post-process it, and then we deal with the estimating the image. But the ideal is that, of course, it wouldn't be useful if we estimate the image and we're estimating the dose, but the dose has already been given, so we can't change it. So the idea is hopefully that this can be done more in like real time, so that we can, as we go through, as we're estimating the image and the dose, that then we can do a better job. But within, because this is just simulations, it's all like post measurement of it. If that, does that answer your question?
No, yeah, that's helpful. Thank you.
Anybody else? Any other questions?
I have a small question. First of all, that's really awesome. That's cool how you got such good results. And also, is there anywhere we can read like a report, or is it going to be published?
Oh, yeah. So there is my like I have a thesis paper that I'm writing that goes along with this presentation. But actually, I have already submitted actually to two different conferences, and they've actually both they're in review and been accepted. That are those two papers are about more the robustness, because as I mentioned, that was the first part, just researching that, and then my final thesis will talk about those things, but also we'll go into all this design, and then obviously along with that I'll have all of my, because I couldn't go into all the details here as much as I'd want to, of all of the like the math that went behind this. But I'm not sure whether who that's released to. Professor Morshett, do you know if is that available to people?
The thesis is not officially posted anywhere, but it's between you and your advisor. You're welcome to distribute it as you wish. It's up to you.
Okay.
Well, I'll just chime in then to say that these things will certainly go into published papers eventually. And as Luisa said, the two papers that are already accepted, those are only about the robustness, not about the actual estimation of lambda. I'll throw in something else too. I'll just say, you know, as a faculty member, I'm less shy about trying to present this as a magic trick. I mean, there's really some magic going on here, because conventionally one would think that you're basically just measuring something proportional to lambda times eta. How the heck are you going to estimate both lambda and eta from only their product? And that's really what this line of work does. It estimates them both, where, you know, most people would think you can only estimate their product. So it's been very gratifying.
Thank you. If there are no other questions, any other questions? Last call. Okay, so thank you, everybody. I'd ask the committee and Luisa to stay.